So the cylindrical coordinate system is, this is how it's defined. Most of you know this. So this is your axial direction right here, right there. And then you have the radial direction and the so-called azimuthal or angular direction. Okay. So the coordinate system is given by r theta z. Okay. Now, very often what happens is, which is what I mentioned here, you want to do, so what happens is things around in this direction, in the azimuthal direction, does not change. For example, if you are doing a pipe flow, it is a fairly good assumption to say everything along the pipe in that direction is uniform. Okay. We're not going to distinguish between little, manufacturing flaws in the pipe wall in this direction. We are going to assume everything is uniform. So that then enables us to get rid of the theta direction and perform what are called axisymmetric, 2D axisymmetric calculations. Okay. So if you do 2D axisymmetric calculations, then this is what your mesh looks like, which is exactly the same as an XY coordinate system. Okay. Except here we are using Z and R. Okay. So the main difference between the area gets bigger. There you go. Okay. As you go in this direction, the areas are not the same. These face areas, this face area versus that face area, if you're looking at the Cartesian coordinate system, are both delta x. Here it's no longer delta x. Here it's, as you know, it's pi r square. It's changing square of the radius. Okay. So this area is getting bigger as we go outward, and in fact the area here is always 0. Even though it actually looks like a boundary, it has 0 area. Okay, the axis of symmetry. So that's the main difference between the Cartesian coordinate system and the cylindrical coordinate system, is that your areas across are changing, okay, in the radial direction. In this direction it's still uniform. Nothing changes. So z is exactly the same as x, but r is not exactly the same as y. Okay? And that, of course, shows up in your governing equations too. So this is our governing equation written in vector notations, but if we now write it in cylindrical coordinates, it looks different. Okay? And the fact that this r is within the derivative here is what is really accounting for your area change. Okay. So that's your governing equation in cylindrical coordinates. And if we do axisymmetric, then this term is gone. No derivative with respect to theta. So we are back to this plus that is equal to that. Okay. And you can see this is like d square phi dx square, but the y derivative is different. Okay. Now, of course, we can apply the chain rule here and rewrite it in a slightly different way. So we just differentiate it through. So this is derivative of a times b, and we have written it as 2 terms. Okay. This part here you can see is exactly the same as your Cartesian coordinates, but now you have this extra term. All right. So if you solve this part here, you would get your Cartesian coordinate solution like you've been getting, but now if you include that term, your solution will be different, obviously. Okay. All right. So in terms of our finite difference formulation, again, same mesh, everything same, starting from I equal to 1 here, I equal to n here, j equal to 1 here, j equal to m there. Okay, no difference. Grid spacings, exactly the same. Delta x is that, delta r is that. Okay. So capital R is the outer radius in this case. So governing equation, this term becomes that. We know that already. Second order error. Z derivative becomes that. Again, second order error. We've already derived all those. Now we got to derive an expression for this guy. Okay. So what do? We do again 2 Taylor series expansions. So we are looking at j j plus 1 and j minus 1. Okay, two Taylor series expansions. One is j plus 1 about j and j minus 1 about j. Again, the same central difference idea, but now our objective is not to derive this guy. Our objective is to derive an expression for the first derivative. Okay, so since that's our objective, we are going to manipulate the equations differently. Instead of adding them, we are going to subtract them, because if we add them, the first derivative will cancel out. Okay, we're going to subtract these two, this one from that one, and that gives us then this. And you notice here that, of course, if we subtract, the second derivative will be gone. Okay, and this is what we are left with, which if we rearrange, we get that. So now we have an approximation for the first derivative, which is also second order accurate, just like all the other derivatives. Okay. Now, this is pretty self-explanatory. I mean, one could have derived this without even going through the Taylor series expansion. You're just using j plus 1 and j minus 1 divided by 2 delta r. Okay, that's what that is. But of course, since we did this formally, we now know what the error is. Okay, and that's an important point there. So that's our approximation. And so when we plug everything back into our governing equation, this is what we end up getting. Okay, now I've written this as Rij, but this can be simply written as Rj, because R doesn't depend on I. Okay, it only depends on J. So Rj is nothing but J times delta R. Actually, J minus 1 times delta R. Because J is starting from 1 at the bottom. So when you plug in J equal to 1, you get 0. Okay? So that's our final 5-band form. Again, we can use any solver of our choice to solve this. Okay? And I mentioned here that just like in the Cartesian coordinate system, the sum of the off diagonals is equal to the diagonal, which is a property of the Laplacian or diffusion operator. Okay. Now these finite difference equations are obviously, as you know, valid for only the interior nodes. So what about the boundaries? What do we do? Okay. So left, right, top boundaries may have Dirichlet, Neumann, or Robin boundary conditions, just like in the Cartesian coordinate system. Okay, and we've talked about this when we did Cartesian coordinate systems. There is no difference. So here is an example of a Robin boundary condition. Robin boundary condition means A dphi dr plus phi equal to C. Okay, it's a mixed boundary condition. Neither the derivative is specified nor the value of phi is specified. If you think this is the first time we are talking about it, no, we have talked about this in, I think, lecture 4 or 5, right after we did finite difference in 1D. Okay, so go back to your notes, you will see that there. So this is the nodal arrangement. We have I comma m at the topmost wall, and then I plus 1m, I minus 1m, and then this is I comma m minus 1. So how do we come up with a finite difference equation for that boundary? Okay, so that's what I'm about to derive. So here is our governing equation. Z direction, this guy, stays the same. Nothing has changed because we do have nodes to the left and right. Okay, so nothing has changed there. R direction, okay, I'm saying first derivative requires no special treatment. You simply substitute in the boundary condition directly. So because you have this expression, so therefore we can say d phi dr is equal to C minus B phi at R equal to capital R divided by A, and that's what I have used here. Phi at R equal to capital R is nothing but phi at I comma m, okay, which is one of your unknowns. That's the node for which you're trying to set up an equation. Okay, so therefore it is okay to have the nodal value in there in your expression. All right, so that's my first derivative, and this R at m is nothing but your capital R, the outer radius. Everybody follow that? So that's first derivative. What about second derivative? Second derivative, we perform a backward Taylor series expansion. Okay. Now here what I'm deriving is a first order accurate expression. If you go back to your lecture notes, we also back to lecture 4 or 5, we discussed also how to derive second order approximation, where you will have to use one more Taylor series expansion. But here I'm just showing you one for the sake of simplicity. So you do a backward Taylor series expansion, okay, in negative r direction. Notice that these are negative, this is positive, okay. And then what you do is, instead of dphi dr, you plug in your boundary condition, okay. That's this guy, the same one that we used in the first derivative. And then you rearrange. Once you rearrange, you get an expression like that. Okay, now of course, as I said, this is first order accurate only. Okay, but it has m and m minus 1, both nodal values. Okay, so that's our second derivative expression, which already has accounted for the boundary condition because we plugged in the boundary condition into that expression. Okay, so boundary condition at this point has been satisfied when deriving this second derivative. Okay, but we still haven't satisfied the governing equation at the boundary. So what do? We take that and we plug it into our governing equation at the boundary. So this is 1 over r d phi dr. This is d square phi dr squared. This is d square phi dz squared equal to your source term. Okay, I think you remember that I had emphasized this, that when you derive nodal equations at the boundaries, you must satisfy both boundary conditions and governing equation. Just satisfying boundary condition is not as accurate. Okay, because we said you're not satisfying the governing equation in the open interval in that case. You're satisfying it in a range much smaller than the full open interval. Okay, so that's what we are doing here. This expression and this expression, we have already used the boundary condition, which means boundary conditions have been satisfied, and now we are plugging it into the governing equation at that node. Okay, satisfying the governing equation at that node. So that gives us that, and of course you can rearrange that to write it in 5 diagonal form. So here's your diagonal, and then you have, essentially in this case, you have 3 off diagonal terms because there is no top one anymore. Okay. Any questions? So it's very important to know the steps to be able to do this, okay? And this is the kind of thing that you will be tested on in your exam. I might give you a boundary condition of a certain kind for a certain problem and say, derive the nodal equation for this boundary, okay? And the fact that you have been only using Dirichlet boundary conditions so far doesn't mean that you do not know how to do other boundary conditions. We have discussed this in class many times, and you have to know how to do all 3 types of boundary conditions. Okay, so so go through the notes, practice that a little bit so you're familiar with it. Okay, and so I said, you know, you can do the same kind of thing for any boundary for that matter, you know, whether it's left or right. I just gave one example here. Okay, now the bottom boundary is very special, as someone here mentioned, that that's really the axis of symmetry. Okay, it is not, you know, a boundary where you can apply an arbitrary boundary condition. And I think that's something that I mean to discuss in the next class. Let's see, I don't think I have that in this lecture. Yeah, so the point here is that one of the issues I just want to point out before we go to the next class is that you run into a singularity right here. Okay, so right here you have a singularity. Why? Because the boundary condition, the symmetry boundary condition, is d phi dr at r equal to 0 is 0. Okay, that's a typical symmetry boundary condition where the derivative is 0. Why? Because if I make the derivative 0, then this value is equal to, this is my axis of symmetry, this value is equal to that value. Okay, that's what the dphdr equal to 0 does for you. But now you have r equal to 0 right there. So you basically have a singularity 0 over 0. Okay. So that requires special treatment, how to do the boundary condition here at the axis of symmetry. And this symmetry, so here's your symmetry boundary condition right here. That's your line of symmetry or axis of symmetry. Okay. Now typically symmetry boundary conditions mean that the gradient of your dependent variable is 0. Okay, as I explained last time, that simply means that whatever value I have here would be the same value that I have here. It's a mirror image essentially. Okay, so that's what symmetry means. So in this case we can say that basically that reduces to dphdr at r equal to 0 is 0. Okay, that's your symmetry boundary condition. So here's our governing equation in RZ coordinates. Okay, I've taken out the theta, so this is just for 2D axisymmetric. And if you now use this boundary condition, the symmetry boundary condition, you see that you basically get a 0 over 0. Okay, because r is 0 obviously, and then dphdr is also 0. So the question is then, what do we do with this term? Because we do have nodes sitting right on top of the axis in the case of the finite difference method. Okay, so we cannot satisfy this governing equation at the axis of symmetry without making any modifications, because we get something that's undefined. All right. So what do? Well, we take limits. Okay. Now remember, I said right at the outset when we started talking about finite difference method, when we were talking about one-dimensional systems, okay, so suppose x equal to 0 and x equal to L, we said that the governing differential equation is valid in the open interval 0 to L. Okay, so that really means that we should apply the governing equation in a limiting sense to the points 0 and L. We should not actually apply it at 0 and L, but only tending to 0 and tending to L. Go as close as possible to 0 and L. Okay, so that's essentially what we are doing here. We are saying, okay, we want to satisfy the governing equation at the axis in a limiting sense, okay, with r tending to 0. So when we do that, okay, now of course we have a 0 over 0. So therefore we apply what's called the L'Hopital's rule. So the L'Hopital's rule, if you remember your math, it's applicable to any quantity where you get 0 over 0 or infinity over infinity. Okay, something that's undefined. It's not applicable when the limit is actually infinity or 0. Okay, it's only applicable when when you get something of this form, undefined. All right. So the way it works is, if you again recall what the L'Hopital's rule says, is it says you keep differentiating your numerator and your denominator successively until you get a finite limit or a quantity that's not undefined. Okay, so what we are doing here is we have a dphdr over r, so we differentiate dphdr and we differentiate r, plug in r equal to 0. And clearly you can see that the denominator, once we differentiate once, we just get 1, okay, the constant. And then the numerator, we get the second derivative with respect to r, which gives me d square phi dr square at r equal to 0. Okay, so therefore in the limit r tending to 0, this quantity 1 over r d phi dr simply becomes the second derivative. Okay. So my governing equation therefore at r equal to 0 becomes that. The first derivative is gone. This becomes the second derivative. Now this is only at r equal to 0. Keep that in mind. Okay. Don't use this equation anywhere else. All right. Any questions so far? So now then the question is, how do we apply our boundary condition? Okay, so just like the wall, all we do is, so this is like a flux boundary condition or a Neumann boundary condition where we have dphdr at r equal to 0. So we do a Taylor series expansion of this node about that node. Okay, so phi I comma 2 is equal to phi I comma 1 plus delta r times d phi dr and so on. Okay, so that's just one point Taylor series expansion. We substitute in the boundary condition which says that this is equal to 0. Okay, so therefore that term is gone and we end up with this equation here, and then we rearrange that. Once we rearrange that, we get this expression for my second derivative. Okay, and of course the error is first order. First order because we used only one Taylor series expansion. If we use another Taylor series expansion, I comma 3 and so on, okay, then we can actually get rid of this term here, and then our error will become second order. Okay, we've done this many times for other boundary conditions. So it's the same procedure. If you want higher order accuracy, you have to use one more Taylor series expansion. But again, the procedure will be the same. In that Taylor series expansion also, you will set the boundary condition equal to 0 or the first derivative equal to 0, and then manipulate the two equations such that you cancel out the third derivative, and then you will get a second order error. Okay, so that's our expression for the second derivative. All right, and then we plug that into our governing equation, the governing equation being this guy here, that after we applied L'Hopital's rule, that's our governing equation. Okay, and once we plug that in there, then that becomes our finite difference equation. Okay, the z derivative stays as is, nothing has changed except you're using j equal to 1 for the second index everywhere. All right, so if I now rewrite it in 5-band form or 5-diagonal form, then we get that. So that's our governing nodal equation for nodes that are sitting on the axis of symmetry.